Start. Okay. Measurement techniques. We talk about accuracy and limitations. Is it more on probes? Okay. A little bit about Q for circuits, calibration, the S parameters, and the vector network analyzers again. So there's kind of two main characteristics of any test instrument, resolution and accuracy. The resolution is the minimum value that you can determine or resolve. So, you know, whatever units it's graded in would be the resolution, which has actually nothing to do with the accuracy. You could have resolution on, say, a micrometer or something down to 10,000th, but it might be accurate to less than a hundredth of an inch.
Doesn't mean it's calibrated.
Right.
You could have great resolution and not be calibrated.
Right. And even if it's calibrated, the accuracy might not be as great as the resolution. In fact, usually the resolution is lower than the accuracy. That's kind of a marketing thing. And the accuracy we define as the difference between the measured and the actual value. So if you measure a standard and you come up with a reading, and the difference between your measurement and what that standard that you measure, and I'm talking mechanical things, but similar to electrical, is the accuracy. And they usually do it in like parts per million. So basically, in the real world, everything has some inaccuracy. It's never going to measure exactly the actual value. And I think that Heisenberg uncertainty means that you couldn't do it regardless, because you're going to affect it when you measure it.
Hopefully not that.
Well, I mean, even in a mechanical thing, if I got a measurement standard and I put a micrometer on it, as soon as that touches it and starts pressing on it, it's going to change the length of it.
How well you're actually seeing it, and I mean everything.
Okay, so and we use frequency counters to measure output frequency on transceivers and other things. The time-based accuracy is the most important part, usually in parts per million. They claim some of them are accurate to 1 part per million, which would be 1 hertz per megahertz, right? So I guess it isn't all that accurate at 1 part per million. If you're measuring a 20-meter signal at 14 megahertz, it means it's off by plus or minus 14 hertz, right? That's more than tuning effect on single sideband. Got an example of measuring a frequency of 146.52 megahertz. The counter has an accuracy of plus or minus 1 part per million. So it means the frequency that you're measuring could vary by as much as 146.52 hertz. And it could be as low as 146.51. So you have to take that into account if you're trying to do any kind of accuracy. In most cases, you're kind of looking for approximate values. But in a lab environment, you care about the accuracy. Or if you were trying to do an alignment on a transmitter or something like that, calibrate it. So which of the following factors most affects the accuracy of a frequency counter?
Bravo.
The time base. It doesn't care about the amplitude as long as it has enough signal to be able to count it. Voltmeters are probably the most common thing you're going to have, whether you're an amateur radio guy or not. If you've done anything with electronics, even AC power around the house, you probably have the DVM. The digital ones nowadays have a very high input impedance. So they have very little effect on the voltage or current that you're measuring, or in this case, voltage. In the older ones where we had volt ohm meters or vacuum tube voltmeters, I still have an old Heathkit one somewhere. You calculate the input impedance by using the sensitivity in ohms per volt. So you take the full scale volts and multiply it by the ohms per volt rating, and that would tell you what the impedance is for that particular voltage range. And that's why they came out with the vacuum tube voltmeters, because they had much higher input impedance or ohms per volt than the standard passive ones. Like if you get the Harbor Freight one for free or for $2.
It doesn't have a internal impedance.
No, it doesn't. That's one of those where you multiply the ohms per volt.
So where would that really come into play when you're taking a resistance measurement or something?
Voltage.
Voltage measurement?
Because on a resistance, well, maybe a little bit, but on a resistance measurement, you're actually sending a current and measuring the voltage drop. So, you know, it's a generator and.
Yep.
But you do have a parallel impedance when you do that. So I'm sure it would affect it some. So you'd want that to be a higher impedance. What's the significance of voltmeter sensitivity expressed in ohms per volt?
Alpha, I think.
Yeah, because you said
Alpha
full
sounds
scale-
good.
Full scale reading.
Those are very wordy answers.
Yeah, it was only down to C when they said alpha.
Is that why sometimes you get a voltmeter, a good one, and you put it on, before you use it, you've got it's 0 volts. But sometimes the last few digits will start just talking nonsense.
Yeah.
Because.
Well, you got test leads, you're picking up noise.
So a good voltmeter is, well, not inaccurate, but it's picking up garbage.
Well, yeah, I mean, depending on how long your test leads are, it doesn't matter how good the voltmeter is. They're gonna act like an antenna if there's RF around.
Well, my cheap old Harbor Freight doesn't do that. It's 0.0.
Well, yeah, but it's not going to as many digits of accuracies
All right, well, all right,
or resolution.
that's the answer. Thank you.
Yeah, the resolution is.
Yeah.
Not even.
But for most cases,
Well, yeah, it's 120 volts, great, you know.
right, you don't care whether it's, 120.1.
Exactly.
Close enough.
Close enough for government work.
But it's probably giving you a reading that's reasonable because it's not.
Yeah,
It's
except
gonna be locked
Oh,
on
no.
120
No, you're right.
volts.
Yeah,
it's not going to be reading true RMS.
true.
The
true.
cheap one.
Yeah, exactly.
But if your house waveform is close to a pure sine wave, it'll be close.
Generally speaking, it's the principle of you get what you pay for.
Oh, yeah.
Or less.
I sleep does one thing, but how afraid they can keep on the boat because they die,
Right. And they're really, really cheap. Sometimes they're free.
Well, $20, that's free nowadays.
Okay,
Except for you, you can get lunch that way. Yeah.
directional power meters and RF ammeters. I don't have an RF ammeter. Do you? Directional power meters measure forward and reflected power. It's kind of magic. They do a couple little transformers in there, and somehow it can determine whether powers are going one way or the other way.
Is this leading up to S?
Huh?
This leading up to S parameters? Or it's-
Well, not directly, but yeah, S parameters are coming up. So they can show you how much power is being delivered to the load by looking at the difference between the forward power and reflected power. So if you're putting 100 watts in, and you're getting 25 watts reflected back, that means that 75 watts was getting to the antenna. And part of that, depending on what the radiation resistance of the antenna is being radiated. Remember we talked about the ratio of ohmic resistance and radiation resistance? So if you got a high ohmic resistance, then that's all loss. It's not being radiated. So it would be the current squared times the radiation resistance, which is actually what's radiated. Okay, so you can calculate the SWR if you know the forward and reflected. And last week, I think we talked about, remember the gamma? Nobody was familiar with the funny gamma sign, which is the reflection coefficient, which is the ratio of the reflected to reverse versus forward power. They call it incident versus reflected or something. So the formula for calculating SWR is 1 plus the reflection coefficient divided by 1 minus the reflection coefficient. And in the case of that example, the SWR would be 1.67. So it would still be acceptable by most people, even though you do have a 25 watts loss. And the reason they do the formula that way is if you assume the reflection coefficient is 0, what's the answer? 1.
But don't they tell you you'll never get 1-to-1? It's always the best it's ever going to be is 1.1 to 1.
Oh, no, it can be less than 1.1. In fact, there may be an example where it's 1.05 or 6. I mean, in theory, it can be 1.0.
Yeah, in theory.
In real world, probably not.
Yeah, 1.1 to 1 is about the best you can expect.
Yeah, 1.1 is pretty good.
So it's reflected power divided by forward power.
Yes, for the reflection coefficient. And then it's 1 plus that divided by 1 minus that. I don't believe that's a test question,
I'm just writing it down, pal.
unless it's one we already did. So how much power is being absorbed by the load when a directional power meter connected between a transmitter and a terminating load reads 100 watt forward, 25 watts reflected?
75 watts.
This is a really hard one. Okay, an RF ammeter can measure actual RF current that's flowing into the antenna. So I guess in theory, as you tune the transmitter to resonance or your power amplifier, the more current, the more power is going to go into the antenna. So, I mean, that's really all it's going to show you is the amount of current. So you would, in this case, you would try to peak the current because it's the current squared times the radiation resistance of the antenna that actually determines how much power you're actually radiating. So what is indicated if the current reading on an RF ammeter placed in series with the antenna feed line increases as the transmitter is tuned to resonance.
More power.
More power.
So you're placing the ammeter right at the antenna?
No, in series with the line.
Oh, in series.
Yeah, because the current's going to be the same at any point, right?
It has to be in line because it's not like a probe.
Right.
It has to be measured in
Right.
series.
Just like your
Yeah.
SWR bridge. I don't know if I've seen any of those that actually measure current. They could, but I guess it's not a popular thing. In fact, I don't have anything that measures RF current. I've got drain current on my transmitter. But that's not necessarily the same thing as what's going out to the antenna. Okay. So sometimes you want to know what the quality factor of a circuit is, not just its resonant frequency. So if you've got a very high Q circuit, you know it's going to have a very narrow bandwidth. The higher the Q, the narrower the bandwidth. And if you look at what we talked about previously on those tuned circuits, how you determine the bandwidth at the 3dB down points or half power points that determine the bandwidth. The wider that is, the higher the Q, obviously. So you can use that to determine the Q if you know the frequency and the half power points. Then you can determine what the Q is. So which of the following can be used to measure the Q of a series tuned circuit?
Charlie.
Bandwidth of the circuit's frequency response.
Yeah, I'm not sure why you want to do that, but it's a test question. Okay, intermodulation distortion. One of the tests, in fact, the only one I've ever heard of is called the two-tone test, where you use two audio tones, typically 700 hertz and 1900 hertz, but it can be any two tones that are not harmonically related. And the only other condition they don't mention here is they need to be very pure tones without any harmonics themselves, because it'll affect the readout. So you apply the two audio tones into the amplifier or the transmitter, and you look at the output. And if you see anything besides those two tones, then you've got intermodulation distortion, which will look like additional spurs popping up at the harmonic frequencies.
I seem to remember one of these two-tone questions on the general, so.
Yeah,
So why two tones?
because it takes two to have intermodulation. I mean, that's the definition. Intermodulation is the modulation between two signals.
Okay.
So it's just kind of a standard test way of doing it. And I guess you can buy a two-tone generator just for that purpose. I would assume it's more like a lab instrument, or you build one. So which of the following methods measures intermodulation distortion in a single sideband transmitter?
Baker.
Read this carefully.
Yeah, you have to read the question or the answer very, very carefully.
So it's
Baker.
Modulate.
Yeah, bench.
Right. Audio frequency not harmonically related.
It's a very wordy one thing.
Okay, vector network analyzers and S parameters. So we talked about the vector network analyzer when we were talking about antenna analyzers. They can measure input impedance, output impedance, reflection coefficient. But in order to use them, you have to calibrate them. Now, the antenna analyzers, you don't have to calibrate every time you use it. At least I know on the Rig Expert, you don't. For the vector network analyzer, you basically need to calibrate it with your setup.
A short, open, and
Right. And you use short, open, and 50 ohms. Now, you could do it at 75 if you had a 75 ohm system, but typically we would do it with short, open, and 50. And those just happen to correspond to the two endpoints in the middle on the Smith chart, which is one of the things that they will display. And that's one of the reasons you calibrate it that way. And that's your normalized impedance for the center. So which of the following can be measured with a vector network analyzer?
all
All the above. Okay, what three test loads are used to calibrate a vector network analyzer?
short, open, and
Baker.
Right. Okay, now the network analyzer measures S parameters. They're called scattering parameters. And it's a little, in the case of a 2-port, it's a 2x2 matrix. So you can reference port 1 and port 2 to input and output. In other words, what you're sending in versus what is being reflected back out. And each one of those parameters, you can display it as the magnitude or the dB value or the phase shift of it relative to the other parameters. And the way they're defined is like S21 means it's what's coming out of port 2 compared to what's going in on port 1. So that would give you the gain or loss through a 2-port network. So your signal from the analyzers going in port 1, you're measuring what's coming out of port 2. So that difference is going to be what the gain is, which can be positive or negative. If you have an S11 parameter, that means that you're measuring what's coming out of port 1 compared to what's going in on port 1, which would be reflection. That's your SWR reading or reflected signal.
so the first one's signal out, right? This first number is the port that the signal's coming out.
Yes. Out versus in. And then, of course, there's 4 of them. There's S11, S22, and S12,
1, 2.
which will do different things.
Right.
And here, maybe I can move this. There we go. It's kind of a neat chart, and it shows you the difference between the incident and reflected for the S11 and the incident and transmitted on S21. And then it shows the other two, the 1-2 and the 2-2, what they would be, which is basically reverse. And you normally use the 1-2 and the 2-1 for 2-port networks, like filters, bandpass filters, high pass, low pass, things like that, or tune circuits. So what do the subscripts of S parameters represent?
Port or ports.
Right,
Alpha.
port 1 or port 2? Now, I haven't seen one, but I suspect you could have a 3-port analyzer to measure 3-port networks, like a circulator.
Charlie.
Forward gain is Charlie. Yep. What is VSWR?
Alpha.
I guess it's technically always VSWR, but we normally say SWR.
Voltage, standing wave.
Yeah. Okay, so
There you go.